Okay, so once again, welcome everyone to this new webinar. Today we'll be talking about the new implementation, the ASD plastic material. And the presenter will be Professor Jose Abel, professor from the University of Los Andes in Chile. You may already know him. He also gave a previous webinar with us, so he doesn't need any further introduction. So just before we start, I will share my screen, and as you may know, we just released yesterday, the new version of STKO, version 4.0. So I want just to summarize some of the new features. Okay. So, well, there are many, some minor bug fixes, some improvements in the Python API, but I want to focus here. And these one are the new things that we implemented in STKO. And of course, the same thing have been implemented in OpenSees. So this new version of STKO goes with, sorry, with the latest version of OpenSees, which is 3.7.0, which has been released, both the official versions and the unofficial version from Professor Tarke. And well, there are many new things, but we put some improvement on the ASD Concrete 3D, some new parameters. The Implex contact element now can also model cohesive zones, so you can add an initial tensile strength and cohesive part to the model. We added a new shell element, which is the triangular counterpart of the ASD shell Q4, which was already present in OpenSees. Then we also added the coupled hinge. We gave a webinar on this one for lamp plasticity, analysis of beam and columns. Then few minor material wrappers, the initial strain material for 3D analysis and the parallel material for 3D analysis. Then the ASD plastic material, which will be the topic of today's webinar. A new constraint handler, because now we were working on a new constraint handler, which is called Auto, which basically mixes the advantages of both the transformation method and the penalty method. So this constraint handler basically imposes SP constraint using transformation. So it will eliminate the equations where an SP constraint is present, while it will handle MP constraints using the penalty approach, which, as you may know, is more effective when you have overlapping MP constraints. I will not go into details. We will do webinars about these new features. Then the ASD Concrete 1D, which is the uniaxial counterpart of the ASD Concrete 3D. What else? Well, some new improvements in the contact element, and some things which are still in beta testing, but the ASD absorbing boundary element now can also update material properties according to the nonlinear property of the soil inside. It has been implemented only on the 3-dimensional version. We are testing it, and it will come soon also for the 2-dimensional version, and a few other things. Okay, but don't worry, we will do webinars on this. So I will stop sharing, and now it's time for Jose to give his webinar. So Jose, please.
There we go. Can you see my screen right now?
Yes.
Very cool. For some reason, I lost the Zoom. I'll leave it there.
Yeah, I can see your presentation.
So, thanks a lot, Massimo, for the introduction. There's very exciting features coming up into both STKO and OpenSees. Very useful stuff. I'm looking forward to those auto constraints myself, actually. I want to thank Asdea Software for this opportunity to give this talk and for the opportunity of doing this development, which has been an intellectually very satisfying endeavor, as I will show you in a while. Thank you, Guido, Massimo, and everybody. And so today we're going to be talking about this new implementation of a wide class of elastoplastic material models, which we call ASD plastic material. So what is it about? Where are we? We are wanting to simulate things which exhibit plasticity, like this little beam here. This video that you're seeing on my screen right now was done with the new ASDPlastic formulation. And we have these increasingly large and sophisticated finite element models that we want to run, and we want to be able to do all types of plasticity, or model all types of plasticity phenomenon occurring here, not just yielding, but eventually interaction between yielding and elasticity as occurs in geomaterials and different type of yield surfaces and the such. So I'm going to talk about the implementation and show a few examples of how this new material model works and how it integrates in both OpenSees and in STKO. So first of all, we need to understand the genesis a little bit of this material. So what are we talking about? A little bit of theory. So when you're doing a large finite element model like the one I just showed in the video, what's going on? There's loads that are being incrementally applied onto the mesh. In this case, it was a force in the tip of the cantilever. And this can be applied in a static sense, in which there's a pseudo time that increases over time and controls the application of the load. Or it can be actual time in the case of dynamic problems. But in a finite element model, there's always this outer loop where you advance some time steps or some concept of time, which gives you an ordered sense of application of loads and damage of the materials and all these things, right? So this advances and you loop here until you reach your final time step. So in this increasing sense, the loads are being applied and de-applied and things are happening, dynamics happens. And then there's an inner loop where the real finite element or nonlinear finite element magic happens. And in this loop is for each time step, we try to satisfy the equilibrium condition in the mesh nodes, basically, of the discretized system. So you apply something like Newton iteration. Okay, so we were here. We were explaining where we are in terms of constitutive models. So there's this outer loop that is the time steps, and there's a little thing here that's bothering me, but it's okay. And then we have this loop where we're trying to reach the equilibrium conditions. So basically what happens here is that the Newton algorithm or whatever other algorithm, what it's doing, it's trying different displacements for the finite element mesh nodes. So that's the U trial. And then out of those, what it wants to form this so-called residual, where it can compare the applied loads with the loads coming from the finite elements. And if those are within certain tolerance, there's a convergence achieved, and then you can take a new time step. But if not, you need to keep repeating this process until we converge. So how do you get from the trial displacement to this trial forces? Well, what happens if you have to loop over all these finite elements, right? So you loop over the elements, you put the trial displacement into the element nodes, and then the element, what's going to do is going to go into the Gauss points and retrieve, or there we go, and get some trial strain. So basically at each Gauss point, you're going to get from the trial displacements your trial strain. And then from the trial strain, you need to compute the trial stress, which is needed to compute the trial forces that we need in the back. So the way to do that is actually through the constitutive model. So you have the constitutive model in between that gives you the trial stresses. And those trial stresses are then taken through the finite element and lumped into the nodes to form what is so-called the trial forces. So this is the big scheme of things in nonlinear finite element modeling, as many of you know. And I just want to point out here that we are deep within the finite element loop in where we're going to be focusing here in this talk. So we're in this red square that you can see there, where we have a constitutive model that's going to take the trial strain and give us a trial stress that we're going to iterate on until we reach that global convergence. Okay, so let's zoom in into the constitutive model, which is the new feature that we're proposing here. Let's go here, advance the slide. So basically, in the constitutive model, we're going to be talking about a wide class of plasticity models in the framework of classic plasticity. I'm going to be using void notation, which is shown in the upper right corner of this slide. And the basic idea is we want to go from the from the last committed stress state, so the last valid time step that we have achieved in previous loading steps, and we want to compute the trial stress based on the trial strain that the finite element solver is giving us. So in order to do that, we need to compute a trial stress increment. This is what the constitutive model is doing. And in plasticity, usually this is the way it's done. The trial strain is multiplied by the current stiffness operator to get the trial increment. Now, this current stiffness operator is thought of as a kind of a tangent stiffness operator here, and it depends on the current state of stress. It depends on a set of internal variables, so these materials have memory. And it depends on some parameters, which might be your elastic modulus and whatnot. Okay, so how does this look like in real life? You specify a so-called yield surface within which, if the state of stress is less than zero, if the state of stress is such that your yield stress is less than zero, your yield function, is less than zero, then you're going to get elastic behavior. But as soon as the equality constraint here is reached, the material is going to be plastic. So if this is less than zero, you only get the elastic component of strain. And if it's equal to zero, you get this plastic strain increment. Areas of the yield function that are greater than zero are not allowed in plasticity. So this is the first component of the material, is the yield surface. The next component is going to be the so-called hardening law, or the flow rule. Okay, so it tells me how this plastic strain is related to a so-called plastic flow rule. So once you're inside the yield surface, your plastic strain is going to be some factor here, so-called the plastic multiplier, that is going to be multiplying this plastic flow direction given by this function m. This m in classical plasticity can also be derived from some sort of potential, but it's a function in general of the stress, the internal variables of the problem, and some parameters. And depending on if you're doing explicit algorithms, your plastic flow multiplier is given by a so-called consistency condition there. You can see the equation, and this equation has this n, which is the current normal to this yield function. So this yield surface depends on the stresses. So you take the stress derivative, so derivative with respect to the stress tensor of this function, and that gives you the n. And m gives you the plastic flow direction that can come from another plastic potential function related to this, or it can be something else. It usually is something else. And then there's this other factor over here, which is the hardening parameter, which tells you how the material hardens. And this can get rather complicated, but this is this scalar is basically the derivative of the yield function with respect to that internal variable, or to the given internal variable. And so I'm differentiating here between two types of variables. So scalar internal variables and tensor internal variables. So if it's df over ds, it's a scalar variable, and this derivative is going to be depending on the current state of stress, the internal variables and parameters of the model, and we multiply that derivative by so-called hardening function that is specific for the material model. And then that gives you a hardening, which is related to the scalar variable s, and then you can add the derivative with respect to a tensor valued internal variable, which with its respective hardening function. Here, this shouldn't be there, but this is okay, like the ht. So it's a different hardening function from this one. And that gives you another component of the classical Elastoplastic framework. You have the yield surface, the flow rule, and hardening laws for your internal variables. And then one final component is how you actually do the integration, because now we can change the equation, the original equation. Now that we know what the plastic strain increment is, given all these equations, now the trial stress is actually just going to be the elastic material matrix. So this is just an elastic, it's not tangent, times the plastic strain increment, and you can use that to integrate. And then the last component is you need to advance the state of your material. So you go from the trial, you go from the commit to the trial, but you also you do the same thing for the internal variables. So if you have a scalar variable, you have a last committed value, and you'll use the plastic multiplier and the hardening function to advance its state. And then you'll do the same for the tensor valued internal variables. So the last component is the actual integration algorithm, which what I have here on display is a simple forward Euler integration scheme, but you can change this part to be an implicit algorithm, or it can be an advanced explicit integrator, like the one we have implemented in ASDPlastic, which is a fourth order Rugnakuta. Anyway, so 4 components: yield surface, flow rule, hardening laws, integration schemes. We can separate this framework into these 4 components. Here's a little example of what this looks like. This is the Drucker-Prager yield function. You might be familiar with it. It's widely used for geomaterials. The yield function looks like a cone in principal stress space. So points inside this green cone are elastic. Points that are on the surface are undergoing plasticity. And if the stress states tries to push beyond the surface, what's going to happen is you're going to develop plastic strains. Okay, so this is an allowed state, any state inside this little circle. This is we're looking at the same yield surface, but in the so-called deviatoric plane. And stresses that are outside that circle are forbidden. So you can't be there in terms of classical elastoplasticity. In some viscoplastic models, it is allowed to be temporarily out of these, but these class of models are not covered right now. Okay, so what about the hardening? The hardening looks kind of like this. If you have isotropic hardening, like what happens is that your yield surface changes inside isotropically, so the same in each direction. And this is accompanied by the development of plastic strains go along with this change. And then the other type of hardening that we can look at today is so-called kinematic hardening. So instead of changing the size of the yield surface, what you change is the location of the yield surface. It kind of gets dragged around. And these 2 processes are called, well, isotropic hardening and kinematic hardening. Kinematic is just the translation of the yield surface. And you can combine these processes to occur simultaneously. So you can have kinematic hardening and isotropic hardening if you so desire. And there's other forms of hardening that are also possible to envision. Okay, so this was a little example. So let's talk a little bit about implementation of elastoplasticity. So usually when you're going to implement this model, if you look at all the plasticity models that have been implemented in OpenSees, they have all these components, but they're kind of hard-coded. You can't mix and match between different options between the components. Now, so you can select that, for example, von Mises yield surface Drucker-Prager, or you can have a flow rule, which is von Mises Drucker-Prager, or you can have all sorts of flow rules, and then the hardening laws. For example, all the boundary surface plasticity is controlled through the hardening laws, and you can have different integrations. So these are components. We should be able to mix and match these components to come up with a wide variety of models instead of single instances of very specific choices of these models. Or this would be something desirable, so to have it to be modular. So credit where credit is due. The first, as far as I'm aware, the first implementation of a so-called modular elastoplastic formulation like the one I'm showing is back in 2002 in OpenSees by my former advisor, Boris Jeremic, and where he basically took an object-oriented approach to programming a wide range of models of Elasto, where you could do this, where you could modularly select different components as you wish, as your heart desires. So you can see in the old documentation and even in the previous versions of the source code of OpenSees, you can see this template Elasto-Plastic material was there, and all the components were selectable. The yield surface had several options, plastic flow potential, all of this comes from way back where. And this was very good. This is a very good thing for teaching, but it had some of its drawbacks. Back in 2002, this is what an implementation of this would look like. This is not the original implementation, but this is kind of the spirit of the idea. So an object-oriented approach to this constitutive modeling. So basically, if you know a little bit of C++, you know about these pointers. So you have pointers, which are kind of references to the different components. And these are wrapped inside a plasticity or a new material class, which inherits publicly from the ND material class in OpenSees. So the object of the class is you specify this set trial strain function which receives the trial strain from the Gauss from the finite element, and you can then call the get stress function, which will give you back the current trial stress. And in between, there's a lot of functions that do the computation and everything, but it will do it depending on how you specify the elasticity, the yield function, the plastic flow, and the internal variables and their hardening. And then you need a base tensor class to represent your stresses and your strains, with which the computations are done. So as good and modular as that implementation was, it was back in 2002, where the current standard of C++ was C++ 98. And basically, you had to work with those compilers back then, right? And the problem with this approach, given more modern C++, is that you had to deal with the so-called RTTI, which is the real-time type inference system in C++. Basically, these pointers, the compiler does not know which specific class, which elasticity you've chosen, which yield function you've chosen, and all these components. So it needs to, in real time, so during runtime, go and figure out which one it's using, get a pointer to the functions of the hardening and whatnot, and then so-called dynamically dispatch those functions in order to produce the computation. And the use of pointers basically prevents compiler optimization. So you have to, at each Gauss point, so remember, we're going really deep into the finite element loops, in the nested loops. And at each Gauss point, we need to be doing this inference of what is my yield function and going back and forth. So in addition to that, the use of pointers actually prevents the compiler from doing some cool optimizations that you can do if you actually know what the components are. And the last problem that it had is that the tensor class available back then was object-oriented and very beautiful because it used index notation, but it was kind of inefficient. So the initial solution, and this goes already to fast forward to 2016, my PhD dissertation, is to use C++ templates. Now, C++ templates actually have been available since 1991 in C++, but the actual language features that allow you to make good use of them are fairly new, even after there have been some significant improvements since 2016. So the basic idea is that you can avoid the use of pointers here. So you can see right here, you no longer have pointers if you use this so-called template syntax in C++. And this is what I did in my PhD. So I used templates to avoid pointers, and I used a little better tensor class for the low-level algebra that is done with tensors. So that's LTensor. Now, the problems I encountered back then, due to both the inadequacy of the standard and of the programmer, myself too, like the lack of ability, is that I could not produce a really modular framework that uses this type of programming because of basically the expressiveness of the C++11 I used back then and template metaprogramming. And this resulted in the need that I needed to have several specific implementation of each component. So a C++ file for each hardening law, for each yield function, for everything essentially, which is a problem when you want to be modular. And the instances, so the particular combinations of these things needed to be handwritten. So you need to write a CPP file for each of the components that you want to mix. And on top of that, the base tensor class did not take advantage of the compiler optimizations because it was not using to the full extent of its abilities the C++ metaprogramming techniques, and also it's no longer maintained. So we had to move away a little bit from this. And here we introduced the ASDPlasticMaterial 3D, which is, again, we're building on top of the shoulders of giants here. Plasticity comes from the early 20th century and it's been evolving since then. And it has a lot of contributions go into this, not least of which is all the advice given by Boris during my stay over there at UC Davis. So ASDPlasticMaterial 3D, what is it? It uses the eigen library for the base representation of tensors, which is a high-performance library, which is actively maintained. The material model is templatized, I'll show you in a second, into its fundamental components, relying heavily on the CRTP design pattern. But we exploit new features of C++14 actually to get a lot of stuff done automatically. So the use of variadic templates for fixed length container class for the internal variables is an important addition here, and trait classes for conditional compilation. And what results from this is a header-only implementation, and this is a really big deal because it means really it's modular. Now we can make it really modular in an easy way. So we have a header-only implementation of plasticity, which in addition to automatically generating all the combinations of materials, we can generate a vast class of these materials. And this automatically takes care of things that previously in the previous standard we could not take care of, like the send self and receive self function for parallel processing. So in terms of number of CPP files, ASDPlastic is one CPP file that is compiled and generates all possible materials, up to 60 or more combinations currently. So let me give you a quick tour of what the source code for this looks like. I'll be very brief, but I just want to show you what this looks like. So similar to what I showed you here, it's templated on elasticity type, yield function type, and plastic flow type, and inherits from the ND materials. There's a lot of template magic here going on that is taking care of the internal variables. And I just want to show you here this set trial strain function that I mentioned before, which computes actually the increment, which then selects the constitutive method that you want to do. By default, we're going into a Runge-Kutta 45 error control, and the reason for this is that we want a very robust integration method that can automatically, without any hassle from the user, adapt to a wide variety of circumstances. This is probably overkill for the majority of the cases, but it's going to work for pretty much anything that you can put in there. And I just want to show real quickly here the function for the, let's look at for example, this is the forward Euler implementation. So you'll find here your check of the yield function, and then if you're in plasticity, you'll compute all these things and compute the trial stress as an increment with and this is all templated. So the cool thing about this is that you need to write the forward Euler just once, and you need to write the Runge-Kutta, just once, and it will be available for all your models. Let me show you real quick what an implementation of a yield function looks like. A yield function is templated on its hardening, on its internal variables. So in this case, alpha is the back stress, and K is the size of basically of the yield of the von Mises cylinder. And you need to specify the yield function, which is this small function over here. And you need to specify the stress derivative, which is this function over here, really small number of lines of codes. And then how to compute the hardening modulus is another function you need to specify. And then there's a mechanism to tell basically the master class what internal variables it's using in here. And then we have in terms of hardening functions, they're also easy to implement. These are all H files, so header files. Linear hardening for tensors, linear hardening for scalar variables, null hardening, Armstrong-Frederick type hardening, and all of these use their. Let me go here into the. Are you guys there?
Yes, we're here.
You guys still there? Okay, now it was my text editor that crashed, but it's not as bad as before. So let me show you some examples of the use of this class. Before that, let me show you what it looks like in OpenSees. So there's this new command available, ND-material, which takes ASDPlasticMaterial specification, and then you produce a tag, and then you have a series of you need to specify your yield function. These are all strings, plastic flow, elasticity, internal variable types, and there's a mechanism. Because this is very, very general, means that the command can get a bit complicated, but here's a little example. So for example, for a Drucker-Prager yield function, we would specify it like this with you specify the constant latency plastic flow direction, and then a linear isotropic 3D elasticity. And the Drucker-Prager yield function and the constant latency plastic flow directions, they actually take two internal variables, and you specify those internal variables, and inside those you specify the type of hardening that's going to produce. And then depending on what you selected up here, you can initialize your internal variables. So we're going to set the von Mises radius to be 1 and the back stress to be at 0. And then you can specify model parameters. There's a lot of flexibility in how to specify these things, and it's basically up to the user to specify them. So let me show you some Python examples of what this looks like. So let's go into a little test here. So this is a Python test. Let's try to do this one. This should work. Okay, so in Python, the syntax is pretty much similar. We have this ASDPlastic, and you specify all your components. In this case, I'm picking a Drucker-Prager. I could select here a von Mises by just changing that line, and you specify all your parameters. And just like any other ND material, you just specify it with all its parameters, and you're done. Internally, what's going to happen, it's going to, from all the models that are available, it's going to figure out whether it's available actually. So if the particular combination of parameters that you chose are available, and if so, it's going to let you do things. By default, all the parameters are initialized to 0. So for example, if you set the Young modulus, if you don't set it, it's going to be set to 0, and that's going to lead to problems. So you need to specify these things, and then you can use the material like any other material in OpenSees. So basically, in this case, what I'm doing is I'm using the ND test, which is a basic strain-driven constitutive tester in OpenSeesPy to test the material. So I am applying strains and getting the stresses out. So I can just run this, and I can take a look at at step by step what the results are. Because this is not nice for an interactive demonstration, I'll show you something a bit better. So I've wrapped this tester facility into a constitutive tester tool that you can use on Python. I won't go through it, but it's the same idea. You drive the constitutive model through strains. So here we are selecting a von Mises yield function and von flow with isotropic elasticity, and we have the hardening set to these variables up here. They're set to 0, and we can take a look at what the response of the material looks like. In this case, don't look at this, it looks ugly, but this is going to be a lot more helpful. So here you can see the strain components. So in blue are the strain with which I'm driving the material, and in orange is the plastic strain I'm reading out from the constitutive model. And on the right-hand side, I have the stresses for each of the components. So I can look at this interactively. This is what it looks like. You have the von Mises yield function and the stress path being plotted in the principal stress space over here. And now I can goof around a little bit with this. What happens if I change the K hardening? The K variable is going to go into the scalar linear hardening parameter, which in turn is the one that controls isotropic hardening. So I can add a little bit of isotropic hardening to this and see what happens. And you'll get these loops are not important, but you see that the stress is opens up like a kind of like a cone, as what I'm showing here in the stress space is the original cylinder, and by the end of the hardening, the cylinder would actually be as wide as the stress that is showing there. So basically, isotropically, when you hit one side of the cylinder grows. Then when you go back, you reverse. You need to wait a little bit more to hit the other side, which is what you see here. And this process continues until the cylinder is large enough so that the response is always elastic. But let's take a look at what happens if I do kinematic. So I change here to 0.1, and you see the behavior. Again, these large plots are not important right now, but you'll see the difference now. So it's the same cone, but what you can see is you produce plasticity on one side, and then that drags the cylinder on out one way. And then when you go back, now you are yielding on the way back before you would be yielding if the cylinder had not changed. So you can move back and forth between these things. Let's go for another test without von Mises. Let's test this Drucker-Prager. Let me see if I set it up correctly. Again, we will not be looking at these ones. Okay, so here's a little setup. And then what I want to show you here is what I have is a Drucker-Prager and a Drucker-Prager plastic flow direction. And what happens is that the material essentially drifts its mean pressure towards the apex of the cone as you go along. So I want to show you here, and the stresses are moving towards 0. So basically, you're losing confinement in a sense. It's as the material is dilating. So so that's because of the volumetric response of this, and I think
with
the Drucker, and this is just showing in other metrics here that are not important right now, but you can see this drift because of the volumetric response of the material, which is due to using the same basically Drucker-Prager plastic flow direction as the yield function basically. So what we can do is we can change that to be a von Mises and be non-associated plasticity in this case. But in the case of von Mises, it's not going to be exhibiting this volumetric behavior. It's just going to be staying in this plane. So this is kind of the basis of how you model the volumetric response in soils, and you can have the material stay within the cone and not lose pressure, and that's controlled by the plastic flow. So this is what we mean when we say it's modular. You can switch around the components, And this is very useful for learning plasticity, but also very powerful to specifying a wide range of material models. Let me show you just one more. Like if you want to have control over that dilatancy, you can use this constant dilatancy plastic flow component, where I change the plastic flow direction to now have a controllable dilatant behavior. So I can control it through that D parameter right there, and you can see that it's drifting towards the apex, but not so fast. And I control that through this parameter 0.1, the D parameter, which is set into as the latency parameter, which is available when you specify this constant latency plastic flow potential or plastic flow direction component. If I set that to 0, the behavior is basically, in this case, it's typical demonstrations. It should be like exactly like phone misses. No, it's not working. Nothing seems to be working today. Because the latency, sorry, I'm not using this D over here. It's set over here. So if I set that to 0, sorry about that, the behavior is totally there's no volumetric response, so it stays right there. So that's that kind of model, and you can mix and match different kinds of models. Let me bring you up a little bit the documentation of this. I had it set up before, but I had to restart. So let's see, is the last really quick, the source. So if you go to the GitHub of the documentation in OpenSees, you can go, it's into the user, sorry. For some reason, OpenSees documentation, source, user. The manual, and then you go into material and the materials, and you can find ASDPlasticMaterial in there, and you can see, for example, well, actually, there's a main ASDPlastic, which is this one. You can see the documentation for this. I can send that in the chat if you want it.
Yeah, just to mention, this one is the documentation in the OpenSees repository, but this one will be compiled by the OpenSees developers, I think in a few days, because they released version 3.7. So this one is the developer version of the documentation, then there is the compiled one, which will be easier to visualize. So yeah, he was showing the documentation of OpenSees. As you may know, in OpenSees, they are migrating the old documentation in a new one based on a GitHub repository. And when there is a new component like the ASDPlasticMaterial, which has been added recently to the repository, the documentation is still under development. So you can still look at the documentation there. The formatting is not the perfect one, but as soon as they release the version 3.7, they will also compile the documentation. So you have the developer documentation and the official documentation. Okay. So if you don't find the documentation of a material, of a rather new material, in the compiled documentation, you can go into the source code of the documentation. Just a side note. I think it's
okay. I just want to end by showing. Maybe we'll do another applications webinar in the future. But just to, in the honor of time, just show the plugin that we were working with Massimo here that allows you to actually use this elastoplastic model in an easier fashion. So you go to Asdea software and you have the ASDPlasticMaterial. I think this is going to be available in version 4, right, Massimo?
yeah, we just released it yesterday, so it's already available for users.
And how about the OpenSees executables? Are they going to be up to date?
There is an OpenSees executable 3.7.0, the official one, and there is also yesterday Professor Tarke compiled his unofficial version of 3.7. So it's up to date. They have this first implementation of the ASDPlasticMaterial. But
Okay.
we are working on it, so we will do new webinars about it because new implementation will come. So this is a start.
Okay, so I quickly just want to show here, I thank the 30 participants that are still with us. It's been tough. It's been tough. So with this new plugin, you can actually test and try the different options in the ASDPlasticMaterial. So in this case, I'm selecting von Mises and the linear hardening function. And let's use a value of 1 here for the von Mises radius. So one megapascal if you want. And we'll use a Young modulus of 1. So this material with the Poisson's ratio of 0, 0, I'm going to be testing, and this is all made up. So the Young's modulus of 1 is super soft, but it's just to test the material. So this should be elastic if I apply a strain of less than 1, essentially. If I apply 0.1, 0.5, sorry, this should actually not yield. So you can see your stress and your strain are linear. But if I try to move beyond that, I should start getting plasticity like the one I'm seeing right there. And then you can, for example, here use this fancy testing tool that Massimo came up with to, for example, do a cyclic analysis that is increasing. And so you do a symmetric, and then you can start playing around with, for example, the scalar hardening options, and to see, for example, in that case, isotropic hardening. And you can try your different options here as your heart desires, essentially. You can also play around with the type of integration. In this case, the model is simple enough that forward Euler can do a good job in running it. And you can play around with the tolerances and the iterations inside. All these options are available for you in there. I think I'll leave it at this, Massimo. Then we can do a more in-depth view of how to use this in the context of actual boundary value problems, which I think it's very interesting.
Yeah. So this one is a first webinar about this implementation, because new things are going to come up here. Jose will be keeping adding new stuff in the ASDPlasticMaterial in OpenSees. So let's say this one is the first implementation. We will be doing new webinars about it. And just to recall the question about the user, for example, this one was a new material. And when you have a new material in OpenSees, for example, in your own version of OpenSees, now let's imagine the ASD material is not in the public repository, it's your own material that you developed. You have two options, actually. One is to use a built-in tool that we have there, which is under ND material. There is a custom ND material, where basically you can specify all the input variables as a string. So STKO will not do any type check on that. And that's the easy way. The more advanced way is to go into Python, because as you know, a part of OpenSea, a part of STKO is actually made of Python scripts that are the interface between STKO and OpenSees. And for example, in this case, we have a Python script under physical properties, which is the ASDPlasticMaterial. And in that case, you can design your own user interface. For example, on the left-hand side, Jose decided where to put all the variables, how to group them into elasticity stuff, variables, parameters, integration options, and you can do also interaction between them. For example, when you select a variable, you can update the others. You can have the material tester tool, or you can further customize it. You can also add new widget, new stuff. So you can use your own custom material. It depends on if you can program in Python or not. If you can program in Python, you can develop your user interface. If not, there is already a built-in simplified function. So yes, I want to thank you again, once again. And if you have any questions, keep in mind we will be doing other webinars about this. So this one is just a first introductory webinar about this new material. So if you have questions, please, we have some more minutes for questions. Thank you again, Jose. Is there any question? I understand this one was a more theoretical webinar, both about theory and implementation point of view. So probably you are you don't have enough questions about it, but in the next webinars, we will be implementing this new material to real problems. And you will see how they behave.
There's I'll try to show something we did regarding boundary value problems. I had a slide here at the end that I want to share with you guys. So the first one was this case that I already showed. Like, we were playing around with this and the hardening and what it looks like. It was and comparing it to what the stress should be at which the cross section fully yields. But in part of testing, it's important to look at benchmarks, which is this other case. So this is a plate. This is a benchmark that Massimo pointed me to. So basically, the difference of the behavior of the material when you're doing a plate and you're doing plane strain formulation or a plane stress formulation, what does the material do in each case? So showing these slides and the differences in the different what happens when the plane stress or the plane strain formulations are yielded. Basically, you get strain localization at a different angle in each case, 35 degrees for the plane strain and 45 degrees in the plane stress. So basically, that's what I wanted to show, that we're already doing some testing here with boundary value problems too.
And also, we have a question here from the user. Is model only applicable to granular soil? Well, I can answer, but I leave the answer to you.
No, well, it's meant to model metals, meant to model, well, as we add components, it's gonna be able to model a wide variety of materials, including geomaterials, soils. But then there's exciting opportunities we want to show you in the future if you start mixing with other components that Massimo has come up with, for example, for this parallel material or the series material. So you can start mixing and matching these models with each other to come up with new constitutive models that previously you wouldn't be able to. So no, I would say it's applicable wherever plasticity is important.
Yeah. Yeah, it's pretty general, so it's not applicable only to one kind of things. And yeah, in the future presentation, we will also show, as Jose was mentioning, how to combine this material with other wrappers that we have in OpenSees. He mentioned the parallel 3D material and the series 3D material. For example, with the series 3D material, you can be creating different instances of simple elastoplastic models. You can develop either multi-surface or multi-L plasticity models without actually coding them. So we will do a series of webinars about this one. So this one was the first implementation, the first webinar, just to show the implementation, a little bit of theory, and the concept of template metaprogramming in C++. The future webinars will be more practical oriented. And I think the next webinar, I will give the next webinar on the new features available in STKO 4.0. And then we will organize other webinars with Professor Jose on this specific aspect, because as he said, this is not just one material. So we cannot do just one webinar about this. Okay, so thank you again, everyone, for taking part to this webinar, and thank you to Professor Jose. And
thank you, Massimo. My apologies one last time.
Don't worry, it can happen. And
Yes.
see you everyone to the next webinar. Bye, everyone.